Good evening. Myself Sanjana MB. Today I will be presenting on priority scheduling algorithm. Now we will know about what is priority scheduling and the CPU scheduling algorithm. CPU scheduling, which plays a very important role in the operating system because it decides which process will execute next. The main goal of the CPU scheduling are to maximize the CPU utilization, minimize the waiting time and the turnaround time, and to ensure the fairness and responsiveness. The only commonly used scheduling technique is priority scheduling. In this algorithm, each process is assigned priority and the CPU always run the process with the highest priority. In some system or lower numeric value means the higher priority, while in other it may be reversed. Priority scheduling, it works in two models: primitive and non-primitive. Primitive, where a running process can be interrupted if a higher priority process arrives. Non-primitive, where once the process starts execution, it continues until its completion. Because of its responsiveness, priority scheduling, it is widely used in a real-time system and operating system kernels. Now let us know about the objective. The main objective of this project is to design and implement a priority scheduling algorithm to apply the primitive behavior along with an aging mechanism to avoid the starvation problem, and to evaluate and compare the scheduling performance using the multiple processes which sets with and without aging, and next to analyze how aging improves fairness by reducing waiting and turnaround time for low priority process, and finally to justify the chosen design based on observation and process metrics. Overall, the goal was not only to implement the algorithm but also to understand its behavior and limitations. Now we will know the flowchart. This flowchart summarizes the working of the scheduling algorithm. First, we take the input of each process like process ID, arrival time, burst time, and the priority. We then initializes the execution parameters such as remaining time and the waiting time. The algorithm runs in a loop until all the processes are completed. At each time step, the scheduler selects all the ready processes and applies aging, which increases the priority of waiting processes. The processes with the highest priority is selected and executed for a one-time unit. When all the processes finish, we generate the Gantt chart and calculate the performance metrics such as waiting time and the turnaround time. Now we will know about the implementation code. So this class which represents the process, this part defines a process object. Each process has the information such as process ID, arrival time, burst time, and the priority value. We also store the extra values like remaining, start time, waiting, and turnaround time, which is used for the final results. Next, coming for this definition function. So this function which performs the priority scheduling with aging, it takes the list of processes and an aging rate. Next, we set the time is equals to 0 to count the completed processes and create a list for drawing the Gantt chart. The while Next we will move to while loop. The loop keeps running until all the processes finish. Next, here we find all the processes that have already arrived and are still not completed. If no process is ready, if nothing is ready, the CPU stays as idle. Next, coming for the for loop, aging increases the priority of waiting processes and preventing starvation. Next, the current equals to max, which is ready comma keep equal to lambda, the x dot priority. This explains that from all the ready processes, the one with the highest priority is chosen to run. Next, coming to if the first time if it's the first time running, we record its start time. Then we run it for one time unit and it reduces the remaining time and move to the clock forward. Next, when remaining time becomes 0, the process is finished. Then we calculate the time turnaround time. Turnaround time we will calculate as completion time minus the arrival time, and also we calculate the waiting time, which means the turnaround time minus the burst time. After that, after that, finally the function returns the updated process details and the Gantt chart sequences. Next, we have some processes. Here we give a sample processes and run the scheduling algorithm. So this code creates the processes, schedules them based on the priority, and it applies aging to avoid the starvations. And it also executes them step by step. Finally, it prints the waiting time and turnaround time, and also it prints the Gantt chart. So this slide shows the program output. We get a table with process ID, arrival time, burst time, and the waiting time, turnaround time. So below that is a Gantt chart showing the sequence in which process were executed. This helps to visualize the CPU execution timeline and the interrupt uh, due to the permission. Now we know the comparative evaluations like starvations, fairness, implementation complexity, efficiency for urgent task, CPU idle time with and without aging. We will now know about the comparative evaluation. So without aging, starvation is a likely low priority process and may never get CPU. And with aging, the possible is low priority process may wait forever. And next, with aging the fairness improves the with it also fairness improves because waiting processes it gradually move up in priority. Next, coming to the implementation complexity. So without aging it is simple and it's easy to code by but with aging it is slightly complex. Next, coming to the urgent task, it's they are still executed quickly, but long waiting task also get the CPU eventually. With aging, it is still good, but fairness may reduce small urgency advance. By next coming to the CPU idle time, in aging and without aging, it is the same in all the cases. But coming to the aging only affects the scheduling order. So next coming to the conclusion. So to conclude the priority scheduling, it is widely used in the CPU scheduling algorithm because of its responsiveness and ability to prioritize the important task. However, the major drawback is starvation. Low priority process may wait indefinitely to solve this. So we implemented aging where the priority increases the longer a process waits. So this improvement gives a better balance between the performance and fairness, making the priority scheduling with aging more suitable for the real-time and multi-user operating system. So after implementing both the versions with and without aging and comparing the using matrices like waiting time and the turnaround time, we observed the aging leads to improve the fairness and reduce the starvation. Um, while the regular priority scheduling algorithm it favors the urgent or high priority task, the version with the aging mechanism it is a better balance between fairness, performance and responsiveness. So based on these results, we can conclude that priority scheduling with aging is more suitable for real-time systems, multi-user environment and long running programs where fairness is important. It provides an efficient, practical, and balancing scheduling solutions and ensures that no process waits indefinitely. Therefore, the enhanced priority scheduling with aging offers the advantage of priority-based execution while maintaining the fairness and preventing the starvation, making it more robust. and a reliable scheduling approach. Thank you.